Mean, variance, standard deviation, and expectation. Calculating the mean and the standard deviation. The discrete probability distribution for the number of girls in a family with 3 children is shown. What is the average number of girls in a family with 3 children? It seems like this average would be 1.5, but it is not possible through experimentation to determine this average. Such a determination would require infinitely many trials of the experiment. Therefore, it is necessary that this average would be determined theoretically. The formula for calculating the theoretical mean for a discrete probability distribution shows that we must sum the products of the values of the random variable and the respective probabilities. So we will multiply each value of the random variable by its associated probability, then add them all together. So we have 0 times 1/8 plus 1 times 3/8 plus 2 times 3/8 plus 3 times 1/8. This calculation gives us 1.5 as the average number of girls in the family with 3 children, as we suspected. The mean of a probability distribution is also called the expected value of the discrete random variable. Expected value is expressed as E of x. So we can also interpret this result by saying that if infinitely many families with 3 children were observed, then we would expect an average of 1.5 girls per family. What is the variance for the number of girls in a family with 3 children? The formula for the variance is similar to the formula for the mean, except the values of the random variable are squared, and then the square of the mean is subtracted from the entire sum. So the calculation will be carried out by squaring each of the values of the random variable and multiplying them by the respective probabilities, then subtracting the square of the mean. This will give us a variance of 0.75. The standard deviation of a probability distribution is found by taking the square root of the variance. So the standard deviation will be the square root of 0.75. This gives us a standard deviation of 0.9 when we round to 1 decimal place. The rounding rule for the mean and standard deviation for a discrete probability distribution is to round to one more decimal place that is found in the values of the random variable. Our random variable values are whole numbers here. So we should round our mean and standard deviation to the 10th place. Calculating the mean and the standard deviation using a graphing utility. A county vehicle inspection bureau recorded the following probabilities for the number of vehicles inspected per day with brakes that do not meet minimum safety standards. The table contains the number of vehicles with unsafe brakes from 0 to 5 and their respective probabilities. In order to use a graphing calculator to calculate the mean and standard deviation for this discrete random variable, we will begin by pressing Stat. Then press 1 to enter the list editor. Type the values of the random variable into list 1 and their respective probabilities into list 2. It is important that the corresponding values of the random variable and the probabilities are adjacent to each other in the list. Now press Stat and cursor over to Calc. Then press 1 for the one variable statistics. We entered the values of the random variable into list 1, so we should press second 1 to specify this list, then cursor down. The frequency list is the list that contains the corresponding probabilities. We entered those probabilities into list 2, so press second, then 2. Cursor down again to highlight Calculate, then press Enter. The graphing calculator then gives us the mean as 1.45 and the standard deviation is 1.56444,878. If you are using a calculator that does not utilize the stats wizard, then you will need to make sure that the syntax is correct. When the screen presents the one variable stats function, you should then press second 1, comma, second 2, then press enter. Remember that the rounding rule for the mean and the rounding rule for the standard deviation are to round to one more decimal place than occurs in the raw data. Our raw data numbers of the vehicles, which are whole numbers, so we should round to one more decimal place. Therefore, we will report the mean as 1.5 and the standard deviation is 1.6. Let's go ahead and follow along with your student notes. The mean, variance, and standard deviation for a probability distribution are comprised differently from the mean and variance and standard deviation for samples. Let's start with the mean. How would you compute the mean number of spots showing up on the top of a die when it's rolled? How many times would it have to be rolled to truly find the mean? Try the mean of 10 rolls, 100 rolls, and 200 rolls. Each would only be a sample which only approximates the mean. You would have to roll the die an infinite number of times, which is impossible. So the formulas from previous sections cannot be used. Let's look at some examples to see why. Suppose we consider tossing a coin 2 times. Let's go ahead and list the sample space. That is to say, if we toss a coin 2 times, we can get either heads, meaning that we got heads twice, heads then tails, tails then heads, or both times tails. There are a total of 4 possible events. Therefore, in the long run, you would expect that you would get 2 heads to occur about 1/4 of the time, 1 head and 1 tail about 1/2 the time, and no heads, which is 2 tails, 1/4 of the time. So on average, the number of heads, the mean distribution, would be 1. Let's go ahead and look at the probability distribution of the number of heads when a coin is tossed an infinite number of times. The probability of getting 0 heads occurs 1/4 of the time. The probability of getting 1 head occurs half the time. And the probability of getting 2 heads when you toss a coin twice would be 1/4 of the time. Let's go ahead and find the mean of the probability distribution to confirm the expected or long time average number of heads. Again, we got 1, but why? As seen earlier in this section, to compute the mean, we take the product of the number of heads times the probability of getting that number of heads, and then add those products up. In other words, 0 times the probability of getting 0 heads, 1 head times the probability of getting 1 head, 2 heads times the probability of getting 2 heads, and then add them all up, and in this case, you'll see we get 1. Now for future reference, let's remind ourselves of the rounding rule. The rounding rule for mean, variance, and standard deviation of a probability distribution is to round the mean, variance, and standard deviation to one more decimal place than the outcome x. The mean of a random variable with a discrete probability distribution is as follows. Note here, once again, we are taking the number in the event times the probability of getting that event, adding it to the number of another event times the probability of achieving that event as well. And we continue along this path until we get to all n events, where again, you take the number of the nth event times the probability of achieving the nth event. When summing up this many terms up to n terms, we can use a very special symbol known as sigma, where x sub 1, x sub 2, x sub 3, and so on are the outcomes, and p of x sub 1, p of x sub 2, p of x sub 3, and so on are the corresponding probabilities. Again, sigma of x times p of x means to sum the products. Let's do an example. Use a probability distribution to find the mean number of spots that appear when a fair die is tossed. Now here, since it is a fair die, we would expect that there is a 1 in 6 chance to get any particular number on the die. And as mentioned from the previous slide, you multiply the event occurring times the probability of that event occurring. So obviously we'd have here 1 times 1 out of 6 plus 2 times 1 out of 6 plus 3 times 1 out of 6, and so on. Multiplying all those out, we get 21 out of 6, which is 3.5. Now obviously 3.5 is not a number on the die itself, but it represents the mean or average number of spots that appear on the die when rolled. Now once again, why is the probability for each of the probabilities 1/6? 1 out of 6 chance to roll any particular number on a fair 6-sided die. Let's take a look at another example. A study concerning the number of trips of 5 nights or more that American adults take per year showed that 6% did not take any trips lasting 5 nights or more. 70% take 1 trip lasting 5 nights or more. 20% take 2 trips lasting 5 nights or more. 3% take 3 trips lasting 5 nights or more, while only 1% take 4 trips lasting 5 nights or more. Let's go ahead and fill in the following chart and then find the mean number of trips that American adults take per year. So the following probabilities will be: for 0 trips, 0.06, 1 trip, 0.70, 2 trips, 0.20, 3 trips, 0.03, and 4 trips, 0.01. Once again, to find the mean, we will add up the products of this probability distribution. Therefore, multiply the numbers that I just circled, then add them up. Once again, here are my probabilities. Summing up the products gives us the following: 0 times 0.06, 1 times 0.70, 2 times 0.2, 3 times 0.03, and 4 times 0.01, giving us an average of 1.23 trips taken per year lasting 5 nights or more. Thus, the mean number of trips lasting more than 5 nights per year taken by an American adult is 1.23 trips lasting more than 5 nights per year. Once again, let's remind ourselves of the rounding rule. The mean, variance, and standard deviation should be rounded to one more decimal place than the outcome. When fractions are used, they should be simplified to lowest terms. From the last example, you'll notice that our data values were based on whole numbers. That is, Americans that would take 0 trips per year, 1 trip per year, 2 trips per year, 3, and also 4 trips per year. Therefore, the mean that we found of 1.23, technically according to the rounding rule, should be rounded to the nearest tens place, that is 1.2. The mean gives a long-run average, but it does not describe the spread of the distribution. Thus, we need to calculate the variance and standard deviation. The formulas from Chapter 3 cannot be used for a random variable of a probability distribution, so we will use a different formula. Now the formula here looks fairly intimidating, and the standard deviation is also just as intimidating. However, in a few moments, I will show you some examples that will make this calculation quite simple, including the use of technology. Once again, sigma squared here is known as the variance. Square rooting the sigma squared is known as the standard deviation. This formula is tedious. So again, in a few moments, I will show you a simpler algebraically equivalent formula and also later technology using a graphing calculator. The simpler formula for variance is as follows. Now again, this doesn't look that simple, but after I do a few examples, you'll realize it's actually not so bad. More importantly, this standard deviation, you simply take the square root. Notice that in both cases, the variance and standard deviations are always positive. Let's go back to rolling a dice. Use a probability distribution to find the mean number of spots that appear when a fair dice is tossed. Earlier, we found that the mean value of this probability distribution was 3.5. Let's go ahead now and find the variance and the standard deviation. Now once again, we simply take the outcome and we square each outcome. After you square each outcome, you then proceed to multiply by their respective probabilities. And much like the mean, once this is done, you simply add up each of those products. So once again, you take the outcomes, you square them, then multiply them by their respective probabilities. Then you add up each one of those expressions, but then at the end, do not forget to subtract by the mean squared. Letting your calculator do all the work at this point, please type this into your calculator. You'll see that you get 2.917 rounded. And since that's the variance, to find the standard deviation, you simply take the square root of the variance. So in this case, you take the square root of the 2.917, and you end up getting 1.708. Now, let's go ahead and find the variance and standard deviation of the previous example that we did, talking about the number of trips lasting 5 nights or more. And let's recall that the mean number of trips lasting 5 or more nights is 1.23. Remember, we will be squaring this mean in a moment and subtracting it from a sum of products. Once again, we actually need to find the square of each of these events. And after you square each event, you will be multiplying times their respective probabilities and then adding them up. Utilizing tables can also be very useful. If you were just to multiply the event times the probability, you'd simply get the following. 0 times 0.06 is 0. But if you were to square the 0, you'd still get 0 times 0.06 is also 0. Likewise, 1 times 0.7 is simply 0.7. 1 squared times 0.7 is also 0.7. Now here's where it starts to get a little bit different. 0 times 0.2 is 0.4. However, 2 squared is 4, and 4 times 0.2 is 0.8. 3 times 0.03 is 0.09. 3 squared is 9 times 0.03 is 0.27. 4 times 0.01 is 0.04. 4 squared, 16, times 0.01 is 0.16. Adding these values up gives us the following. 1.23, which is the mean, very familiar, and 1.93, which will help us find the variance. So now solving for variance, we do the following. Simply take the 1.93 and subtract 1.23, but don't forget to square the 1.23. That should give us 0.4171. Here, I invite you to pause the video, type this calculation into your calculator, and make sure that you get the same value as I have. Then, of course, standard deviation, take the square root, which gives us 0.6458. Now let's go ahead and learn how to use our graphing utility. First, press Stat, then select 1, the Edit list. Upon selecting Edit, enter the values of the outcomes x into list 1, and the values of the probabilities p of x into list 2. Notice here I'll be using the same numbers from the previous example. Pause the video and please do the same. Then press Stat, use the right arrow to choose Calc, and then select one-to-one variable statistics. Enter list 1 for the list and list 2 for the frequency list. Then calculate. You will notice here that the mean is 1.23 and the standard deviation is 0.6458. If you wanted to find the variance, simply take the 0.6458 and square it. Expectation. Expected value or expectation is used in games of chance, insurance, and other areas such as decision theory. Expected value, denoted by E of x, is another name for the mean of the distribution. Thus, the formula is as follows. In gambling games, an expected value of 0 indicates a fair game. If the expected value is negative, the game favors the house, and the player will, in the long run, lose money. If the expected value is positive, the game favors the player, and the player will, in the long run, win money. Let's go ahead and try an example based on expectation. A person pays $3 to play a certain game by rolling a single die once. If a 1 or 2 comes up, the person wins nothing, effectively losing the $3. If, however, the player rolls a 3, 4, 5, or 6, he or she wins the difference between the number rolled and $3. Find the expectation for this game. Is the game fair? If the player rolls a 1, that means the player lost $3, and the probability of rolling a 1 is 1 out of 6. Therefore, we begin our expectation by multiplying -3 times 1 over 6. And now we're going to add that to the fact that if they roll a 2, they also lose $3. And again, the probability of rolling a 2 is 1 out of 6. Now, however, if they roll a 3, they win the difference between that number and the $3, which in this case, 3 minus 3 is $0. And the probability of rolling a 3 is 1 out of 6. If the person rolls a 4, 4 minus 3 is $1. They gain back $1. Multiply that times 1 out of 6. Then add it to the fact that if they rolled a 5, they win $2. Again, 1 out of 6 chance. And finally, add it to rolling a 6 gives them $3, multiply by 1 out of 6. Calculating all these numbers and following the order of operations will in fact give us 0. And since, in the long run, the player will not lose any money, the game is fair. Once again, notice this is just like finding the mean of a probability distribution. Expectation and mean go hand in hand. Let's go ahead and show one last example that calculates expectation. An insurance company insures a person's antique coin collection worth $20,000 for an annual premium of $300. If the company figures that the probability of the collection being stolen is 0.002, find the company's expected profit. Let's take a look at the probability distribution. The company has a 0.002 chance of losing $19,700. Remember, the customer has already paid $300, but they stand to gain $300 at a much higher probability. What is their expected profit? What we do here is we multiply the potential loss times the probability and add it to the potential gain times its probability. Here we get negative 39.4 plus 299.4, giving us a total of 260. Notice that's a positive result. Therefore, their expected value is $260. That is, the insurance company expects to gain $260 from this transaction.